do that now. Good. So in this case, we have a battery connected to a resistor, connected to a capacitor, all in series. So using our Kirschkorn loop rules, we came up with this expression. So we have the EMF minus the current times the resistance, so that's Ohm's law, minus the charge divided by the capacitance, so that's for capacitors, is equal to 0. Here we solved our integral, and we found that the charge as a function of time was equal to capacitance times the EMF times 1 minus e to the minus t divided by tau, where tau is what's known as the time constant, which in this case is RC. And then the current is the derivative of that guy, so that's E over R times e to the minus t over tau. For discharging, we didn't actually formally talk about this, but in this case, we would simply have a resistor connected in series to a capacitor. So here I would start off with this guy. Here's my capacitor. So in this case, the only thing that's going to be different was here we're charging the capacitor. So initially we have 0 charge, and then this thing is going to charge up to maximum charge. Where here we're going to start off with some initial charge. So let's say this is the positive plate. This is the negative plates. So what will happen in this case then is that the positive charges will move through our circuit, creating a current for all the positive charges then to move to the negative plate. And then that'll eventually cause this charge to go to 0, this charge also go to 0, which causes the current to go to 0. So in this case, we then have these two expressions. So they're both just exponentially decaying in time. So the charge goes from the initial charge down to 0, current goes from the initial current down to 0, and time constant is still the same. Now, one thing to note here is that these are only true when these things are in series. So this is only true when in series. If I have anything else, I then have to use different Kirschkorn loop rules to find then these different expressions, but they're going to look something similar to these guys. Good. So now that we talked about those, last thing we have to do is do a couple examples of these just to get a little more familiar with them. And then we can do a review for Friday. And again, just to let you know, Thursday, again, tomorrow, we're going to go ahead and start new material just to get a little bit jump start on that. So we'll talk about magnetic fields and stuff tomorrow. So good. So the first example says, take that the capacitance in our usual circuit here. So again, here's our EMF, our resistor connected to our capacitor. So our capacitor has 0.3 microfarads worth of capacitance. The resistor has 20 kilo ohms worth of resistance, and EMF has a battery of 12 volts. So in this case, we want to determine part A, the time constant, part B, the maximum charge the capacitor could have, C, the time it takes for this thing to reach 99% of the maximum amount of charge, and then D, the maximum current flowing through our system. So these are the things that we want to find. So let's look at those things. Next, good. So again, so here we know that our capacitance is 0.3 microfarads. We know the resistance then was 20 kilo ohms, and our EMF was 12 volts worth of potential. Good. It doesn't look like a 3. Looks like a something. There we go. There's a 3. Good. So good. So part A, we simply want to know what's the time constant. So what is tau? Well, as long as these guys are connected in series, we know tau is simply going to be R times C. So this is just going to be our resistance, which is then 20,000 ohms. This thing has to be in ohms, times the capacitance, which is 0.3 times 10 to the minus 6, because this has to be in farads, not microfarads. So this is then going to be, what, 6 milliseconds, right? That's okay. It's 6 milliseconds, right? Yeah. So 6 milliseconds. Good. Nice and easy. Part B then wants to know, what is the maximum amount of charge that this thing can hold? Right? So there's two ways to think about the maximum charge. The maximum charge is going to go when the current is going to 0, which means the maximum charge then is simply equal to when the resistor has 0 current running through it, which then should be equal to the capacitance times the EMF. Or another way to think about it is we know the charge is equal to the capacitance times EMF, E minus 1 minus e to the minus t divided by tau. This thing is maximum when this term goes to 0, which then gives us the same thing. So either one is fine. So in this case, the maximum charge is simply the capacitance times the EMF. So Q max then is equal to 12 volts, that's our EMF, times our capacitance, so that's 0.3 times 10 to the minus 6. And that's going to be what? Farads. So that's going to be what? 3.6 microcoulombs. So this is my maximum amount of charge. So this is Q max. Assuming I can multiply. Okay, good. Okay. Everyone's okay? Not too bad so far. So the next part then says, what then is the time it takes for this thing to reach 99% of the maximum charge? So we're looking for that Q then is equal to what? 0.99 times then Q max. So this is what we want the charge to be. So this is the charge then on the capacitor. Well, we know the charge is related to time by Q max, because that's C times E, times 1 minus E to the minus T divided by tau. So since the charge in this case is going to be 0.99 or 99% of Q max, then it has to be equal to Q max times 1 minus E to the minus T divided by tau. So the Q max are going to cancel, so we don't actually care what Q max is. So we get 0.99 must then be equal to 1 minus E to the minus T divided by tau. So now I'm going to add this term over here and subtract this term over here. So I get E to the minus T divided by tau is equal to 0.01. I want to get rid of this negative because I want the time. I don't want negative the time. So I'm going to take 1 over each one of these. So remember, this is the same thing then as 1 over E to the T divided by tau. So I'm going to cross multiply. And this is the same thing as 1 over 100. So I'm going to get 100 then is equal to E to the T divided by tau. And how do I get rid of an exponential? So what's the mathematical process, which is the inverse of an exponential?
Natural log.
Natural log. Good. So I'm going to take a natural log of both sides. So let's go ahead and do that. So I'm going to get natural log of 100 then is equal to the time divided by the time constant. Or finally, this says that the time it takes to reach 99% of the maximum charge is going to be the time constant times the natural log of 100. So this is the time it's going to take. Plug in my numbers. This is, again, what? 6 milliseconds times natural log of 100. So this works out to be about 28 milliseconds. So the time it takes for this thing to reach 99% of its maximum charge is very quick. So 28 milliseconds. This was what, part C, right? Good. Nice and easy. Nice and easy. Part D then says, okay, so part D, we now want to know what is the current when the charge is half of its maximum value. So we want to know what's the current when the charge equals half of its maximum value. So we know what is the current when Q on the capacitor is equal to half of Q max. So this is what we want to know. Good. So in this case, easiest way to solve this one is to actually use that E minus I times R minus Q over C must be equal to 0, right? This must be true at any point in time. We got this from Kirschkorn's loop rules, so this must be true for any time t. Good. So here we know the EMF, we're looking for the current, and we know the charge. The charge is simply going to be half of the maximum charge. So we can rearrange this thing to then solve for the current. So let's solve this for the current. So this says the current then is going to be equal to 1 over the resistance times the EMF minus half of Q max. That's right, this says Q max divided by 2 divided by the capacitance. Right? Now again, we know Q max is simply equal to what? CE. So this is going to be the same thing as what? CE divided by 2E, but this C is going to cancel this one. So this is going to be E minus then E divided by 2. So this is going to be equal to 1 over R times E minus E divided by 2. But E minus E divided by 2 is the same thing as 1/2 of E. So this is going to be equal to what? E divided by 2 times R. So this is going to be the same thing then as 12 volts divided by 40,000 ohms, right? Because the resistance is 20. 1,000, but then multiply that by 2 gives me 40. So plug that in. We get in this case then is this works out to be 300 microamps. So this is the current running through the resistor when the capacitor has half of its maximum charge. It's okay. Not too bad, right? So the next part then, part E says, okay, what is the maximum current? So what is Imax? Well, Imax is given by when the capacitor has 0 charge on it, so the capacitor doesn't act like it's there, which means it's by Ohm's law, simply the potential divided by the resistance, or in this case, EMF divided by the resistance. So this is actually then just going to be 600 microamps, right? It's twice of the previous value that we just found. Finally, part F says, what is the charge when the current is half of its maximum value? So in this case, we want to know what is the charge on the capacitor when the current is equal to 20%. Did I say half? Sorry, I meant 20%. 20% of its maximum value. Okay, so we want to know how much charge is located on this guy. So again, the easiest way to do this one is do exactly the same thing we just did in the previous part, which take that the EMF times or minus the current times the resistance minus the charge divided by the capacitance must be equal to 0. Now, just like in the other part, this is not the only way we can do this. We can also use going back to how the charge and the current depend on time. So in this case, what we could do is we could find the time it takes for this thing to reach 20% of its maximum current, use that time back into the charge expression, and then find the charge it has at that given time. So that's another way that we could do that. The only problem with that one, I don't want to say a problem, it's going to work just as fine, but the only thing that's different is that takes multiple steps, because first I have to sign all from the time here, use that time back into here. So there's a lot of things that can kind of go wrong. This one's a little bit more straightforward. So let's just use this one. So good. So this says then, let's solve this for the charge. So the charge then is going to be the capacitance times the EMF minus the current times the resistance. Here, this is specifically at 0.2. So we want the capacitance times the EMF minus 0.2 times I max times the resistance. But again, we know I max is simply E divided by the resistance. So this resistance here is going to divide this resistance. So this is going to be equal to 0.8 times the capacitance times the EMF. Good. There we go. So this is just at 80% of its maximum charge. So this is going to be at 80% of then Q max, which then works out to be 2.9 microcoulombs. So good. So this is the charge when it's at 20% of maximum current. Everyone's okay? Not too bad, right? So let's do one more example. So the last example says that we have a typical turn signal flashes twice a second, meaning that the time constant is 0.5 seconds. The RC circuit controlling this may have a capacitance of 1 microfarad. What then is the resistance? So this is a very simple question. So in this case, we know the time constant, and we know the time constant is simply equal to the resistance times the capacitance. We know the time constants, we know the capacitance. We're simply looking for the resistance. So the resistance then is equal to the time constant divided by the capacitance. Plug in our numbers. This works out to be 500 kilo ohms. So this is our resistance. So nice and easy. Not too bad. So I'll leave it that way. So everyone doing okay? Not too bad. Everybody's faces. Good. So that's it. We are now done with everything for the exam. So the only thing we have left now is to do a review. So not too bad. So let's do a quick review and then let's talk about the exam. Good. So first things first is chapter 26. So chapter 26 is, we technically have some stuff that carried over from exam 2, and that's some of the potential and electric field relationships. So first things first is remember that the change in potential is related to the electric field by minus the integral from A to B of the electric field dotted by the differential length. And then from here, this tells me then that the electric field is equal to minus the gradient of the potential. So this is in 3D. Or if I'm looking at 1D, this is then equal to simply minus the derivative of the potential in some direction, let's say the x direction, in the I hat direction. So this would be in 1D, specifically in the x direction. Okay. So again, this one says that if I know the electric field, I can then determine the potential between 2 points, given this way by integrating over the electric field. This one says if I know the potential at every point in space, I can then find the electric field also at any point in space, or at least throughout the entire space. And then when I know specifically the point I want, it is evaluated at that particular point. The other thing from this chapter that had to do with potential was the potential of a continuous object. So if this is my continuous object, again, we chop this thing up into a small chunk here. So this is going to be my dq. If this is my point out here, let's call this point P. Then the distance r, do that in blue, is the distance from dq to the point P. So this is r. Remember, this has no spatial, has no direction, it's a scalar quantity, so we don't have to worry about any directions or anything. And what this says then is that the potential at point P then is equal to the integral, so I have K, integral dq over R. Now, again, this thing is a scalar quantity. K is the usual K, so this is the 1 over 4 pi epsilon naught. Epsilon naught, which is equal to the 9 times 10 to the 9th. Let's see, what is this? So this is a Newton meter squared per Coulomb squared. And again, we're integrating this thing, so dq is one of 3 things. So this is either lambda dl when I have line symmetry, eta dA if we have area symmetry, and then rho dV if we have volume symmetry. Right. So again, here you would just simply turn dq into an integral over geometry, depending on what type of geometry that I have. So it'd be one of these different 3 things. And remember, this is actually technically a potential difference. So this is the potential difference between the point P and spatial infinity. So I'll write that over here. So this is the potential difference between point P and r equals to infinity, where again we know that the potential at infinity is equal to 0 by definition. Okay, so that's where our potential goes to 0. So good. So these are the things that kind of carried over from the previous exam to this one, but that's fine. So the next thing we looked at were capacitors. So let's talk about capacitors. So here, remember, capacitors are 2 conductors. So here's one conductor, here's a separate conductor, where these guys are separated by some spatial distance of d. And then here, what we said is we apply potential difference across these guys. So here's my potential difference, put a battery on here. So this is my delta V. Then in this case, the charge that builds up on the positive plate is then related to the capacitance by the potential difference. Okay. Most of the time, I'm going to write this as simply C times V, where I'm going to write delta V is equal to V. So in this case, it just means that I'm setting one of these plates at 0 volts, and then the other one is at whatever the voltage is. So my change of potential in that case is simply the potential of, in this case, the top plate. So that'd be the positive plates. So from this, what this means then is that capacitance by definition is then equal to the charge divided by the change of potential across the plates, or again, the charge divided by the potential. Okay, so this is the capacitance by definition. Again, the first one's just saying if I plotted the potential versus the charge, I get a straight line. That straight line slope is equal to the capacitance. So the capacitance of the capacitor. One noteworthy capacitance that we found using this guy was the parallel plate capacitance. So if I'm dealing with a parallel plate capacitor, the capacitance then is equal to epsilon naught times the area divided by the distance. So this is my capacitance of a parallel plate capacitor separated by distance d. So here are my parallel plates. Each plate has a cross-sectional area or just an area of A. And again, these guys are separated by a distance of d. Sorry, thought I heard my son scream. Okay, numbers okay? Good. So from here, we then looked at, well, what happens if I have a different capacitance that I need and I don't have one of those? So how do we add these guys together? So we looked at parallel and series. So parallel and series. So what we found was that in parallel, there we go. What's the same is the voltage. There we go. Yes.
Hey, Daddy, look at this.
Thank you.
Nobody can do that.
That's right. Nobody can break dance like that. That's right. So I have 1 over the equivalent. Oh no, what am I doing? That's the wrong one. So in parallel, I have the equivalent capacitance then is equal to the sum over all of the capacitors. And then in series, what's the same is the charge. And then here, 1 over the equivalent capacitance is then equal to the sum over the inverse of all the capacitances. So again, here, this has the effect of increasing the overall capacitance. This has the effect of decreasing the capacitance. This looks like a 3rd grader wrote that. Let me get rid of that. Mildly better. Okay. Good. Now, the other thing we said was that the main purpose of a capacitor is to store energy. So what's the energy that this guy can store? Well, the amount of energy that this guy can store, so we call that U stored, is equal to the work done it takes to charge it, which is then equal to 1/2 of, so either Q squared divided by C, so the charge squared divided by the capacitance, the capacitance times the voltage squared, or the charge times the voltage. So either one of these is fine. Or we said we can look at what's known as the energy density, which is the energy per unit volume. So we write that as little u, which is then equal to big U divided by the volume, which is then equal to 1/2 epsilon naught times the electric field squared. So here we just said that the energy then is stored directly in the electric field. Here the energy is stored in the charge. Here the energy is stored in the potential. Here the energy is stored in the potential and the voltage. So any one of those is fine. And the last thing we looked at was dielectrics. So remember, a dielectric is an insulator which has a breakdown potential which is greater than that of air. And then the dielectric is classified by the strength of the dielectric constant, which again is the ratio between the breakdown potential of the insulator versus that of air, which is called kappa. Right? So this is our dielectric constant. So kappa, remember, is kind of the Greek K there. So this is the dielectric constant, also known as the dielectric strength. So we said the primary purpose of this was that when we add it to a capacitor, this increases the capacitance of the capacitor by a factor of the dielectric strength or the dielectric constant. So here the capacitance increases by kappa, and then C0 here is the original capacitance before I put in the dielectric. So C0 is without dielectric. Now, what this did and how it affected the circuit depended on how I inserted it. So here we inserted it one of two ways. So either it was connected to a battery, so if it was connected, or if it was disconnected from a battery. So let's talk about each one of those two cases. So when it's connected to the battery, what had to happen was that the new potential was equal to the old potential because the potential is fixed by the battery itself. The electric field actually then between the plates then decreases because I get a polarization with the dielectric, which means I can put more charge onto it to bring the electric field back up to the actual place, which means that the charge is equal to the dielectric constant times the original charge. Which also means then that the energy stored is going to also increase by a factor of dielectric constant. As well, like an R. Good. So that's what happens. Oops. For when it's connected. So the energy goes up, the charge goes up, but the potential remains the same. When it's disconnected, what happens in this case then is when I insert the dielectric, the charge now remains the same. But since the electric field has now decreased because of that polarization from the dielectric, what happens now is the potential then will decrease by a factor of the dielectric constant, which means the electric field also decreases by a factor of the dielectric constant. And the energy also decreases by a factor of the dielectric constant. Okay. Now, both of these are only true when I am inserting the dielectric. So these are true when we are inserting dielectric. Now, if I pull out the dielectric or I remove it, these things are then opposite. So what happened then is that the charge would go down, the energy would go down, here the potential would go up, and the energy would go up if I pulled it out. So just the opposite would be true. So good, so this is all chapter 26. So now we can start talking about chapter 27. So chapter 27, we started looking at Ohm's law, so currents and resistors and all that kind of good stuff. So first we can look at currents. So we said current then, by definition, is equal to the change in charge divided by the change in time. Or we have the instantaneous, which is then equal to the time rate of change of the charge. So again, in both of these cases, we just said, here's a wire. We're cutting out some cross-sectional area. That cross-sectional area then is A, and we're counting the number of charges which pass through this cross-sectional area as a function of time. So over an amount of time, this then is the number of charges which pass through. Then we said that if we plotted the potential across an electrical element versus the current, in this case, we would get simply a straight line, which is then equal to the slope is equal to the resistance. So here, this is Ohm's law, where Ohm's law says that V is equal to then I times R. Now again, remember with Ohm's law says that this is only true for conductors. If I don't have a conductor, Ohm's law does not work. Resistance, we said, is basically what? The collisions that the object is making inside of the wire. So in this case, we have the resistance is equal to resistivity times the length of it divided by the area. So remember, this is our probability of death. So here's my circuit element or my wire, whatever it happens to be. Here are the atoms on the inside. And again, we're supplying an electric field across here. So here's my electric field. I'm then trying to accelerate these charged particles through here. Let me use yellow. But these guys are constantly colliding, making elastic collisions. These elastic collisions then are causing it to move with a drift velocity, an average velocity going through the wire. From here, we talked about the microscopic version. So we had the drift or the current density. So the current density, at least the magnitude of it, is equal to the current per meter squared, which means that the current is equal to the integral of the drift velocity, or sorry, not drift velocity, current density dotted by the differential area. So this is our current in terms of current density. And dA, we said for our purposes, is going to be equal to 2 pi r dr in the r hat direction. So this is our dA. So again, current is the average over the entire wire. Current density is talking about what the current is actually doing from location to location. In terms of the drift velocity, we then wrote that the current, there we go, is equal to the charge times the number density times the cross-sectional area times the drift velocity. Remember, N here is equal to charge particles per unit volume. So this has units of 1/meters cubed. So this is our current, our number density. So it's the number of charge particles per unit volume. From here, we can get the current density. Current density then is equal to the charge times the number density times the drift velocity. From this, we can then have that's what? The current density is related to the electric field by the conductivity, where the conductivity is equal to 1/resistivity. So I can also write this as rho times J is equal to the electric field. So it just says that the direction of the current density is in the same direction as the electric field, since rho and sigma here are always positive quantities. So this is my conductivity. The last thing is, as the charged particles are trying to move through this wire, colliding with these atoms, as it collides with the atoms, then it gives up some of its energy, its kinetic energy, then to the atoms inside of the wire, causing them to vibrate even faster and faster and faster. And then kinetic theory says that as those guys gain kinetic energy, they also radiate away energy via thermal energy, which is what's called power loss. So power loss is then equal to I times V. So this is the current times the potential across that object. But that's also equal to the current squared times the resistance, and also equal to the potential squared divided by the resistance. So any one of these three are equally useful, but these two are specifically for resistors. The top one is used for any electrical device, doesn't matter what it is. And I believe that's the end of chapter 27. So now we can move on to chapter 28, which is the last chapter. So chapter 28, we talked about resistors in parallel and series. So resistors in parallel and series are the opposites of conductors, or sorry, not conductors, capacitors in parallel and series. So again, in parallel, what is the same is still the voltage or the potential. But here, instead of we're adding the capacitors together, we're inversely adding the resistors together for the equivalent resistance. For series, what's the same now as the current instead of the charge, but we know current is simply moving charge, so those two things are the same. But now we're going to add the resistors together to get the equivalent resistance, which means in series, the resistance goes up, and parallel, the resistance goes down, opposite to the capacitors. Now, again, this only works as long as I have one battery, or at least not a battery in the general vicinity of these things. So if I have more than one battery, we then have to use Kirschkorn's rules. So Kirschkorn's rules are two rules. So rule number one is the loop rule. So again, the loop rule says that if I start off at a point and I go back to that point, the change of potential from that point back to that point, which I'm going to write as A to A, is then equal to 0. So just the change of potential through any loop must be equal to 0. Second loop is then what's known as the junction rule, which is conservation of current. It says that at any junction, the sum of the currents coming in must be equal to the sum of the currents going out. So again, if I have all currents coming in and nothing going out, I don't satisfy the junction rule. So therefore, that is not a suitable circuit. So I have to start all over again. Associated with these guys are a few signed rules. So let's talk about the signed rules here. So our first signed rule is for, let's say, batteries. Do opposite of usual. So for batteries, I have here's the negative plate, here's the positive plate. So negative, positive, EMF. And this is, say, point A, and this is point B. Then the change of potential going from A to B is then equal to positive EMF. So in this case, I'm going in the same direction. I'm going this direction from negative to positive. But if I go the opposite direction from positive to negative, then my change of potential going from B to A is then minus EMF. For resistors, we then have, so here's my resistor. So A, B, in this case, let's say the current is going this way. So this is my current. So if I go in the same direction as the current, then my potential difference going from A to B is then minus I times R from Ohm's law. But if I go the opposite direction of the current, then my change of potential going from B to A is then plus I times R. So I have a potential increase in this case. Capacitors. So let's do capacitors over here. So for capacitors, again, let's say here's point A, here are my plates. Good, this is A and B, plus, minus, capacitor. So in this case, if I go from the positive plate to the negative plate, then my change of potential going from A to B is negative Q over C. But if I go the opposite direction from the negative plate to the positive plate, then my change of potential from B to A is positive Q over C. Okay. So these are all of our sign rules. Again, here we have our steps. I'm not going to write down the steps, they're in your notes. But again, we have those 6 steps. Again, identify the loops, write down the currents, choose directions, apply the loop rule, apply the junction rule, solve. So these are all of our steps. Finally, the last thing is the RC circuits. So for RC circuits, we've now seen charging particularly. So charging again, we have E minus I times R minus Q over C equals 0. Or again, this is just an application of Kirschkorn's loop rules. And again, this is only true when everything is in series. Then we have the charge as a function of time is equal to C times E, 1 minus E to the minus T over tau. The current as a function of time is equal to E over R, E minus T over tau, where again, tau is R times C. For discharging, here we now have Q as a function of time is whatever the initial charge is, E to the minus T over tau. And the current as a function of time is whatever the initial current is, E to the minus T divided by tau. Or again, tau is the same thing. R times C, again, is only true when they're in series. So that's it. Did everybody get that? Anything you want me to go back to? No, he's doing okay?
Quick question.
Sure.
On the charging, you say it's like the E minus I R minus Q divided by C is only for in series.
Yes.
Can you just make the capacitors in series if you gave us like parallel, and then just do with the formula?
Well, it depends on how I connected it. Okay. So what you're saying would be true, yes. If I had something like, so let's go back. So yeah, if I had a battery connected to, say, a resistor, connected to, say, one capacitor here, another capacitor over here, which are in parallel. If I had something like this, then yes, you could then just combine these two together in parallel to create one equivalent capacitor, and then that would reduce down to this, where this would just be the equivalent capacitance. That'd be absolutely correct. But sometimes it's not going to be quite that easy. Of course, I'm not going to do this to you. But so, for example, if I had like a mixture, let's say I put a resistor here with a capacitor, and then I kind of mix these guys together. So a resistor here with another capacitor, and then I could put another stuff over here. So it becomes a little more complicated in this case, because now I can't really add these guys in parallel in series anymore. So what you would have to do is actually apply Kirschkorn's loop rules across each loop and actually do it that way. Does that make sense?
Yeah.
Good. So yeah, so basically I would just have to set up Kirschkorn's loop rules, get equations that look something like this. Use the fact that, again, I is equal to dq over dt, do the separation of variables and all that stuff that we did before, and then basically have to solve it that way. This is, not to scare you, something I did do in the past, but I don't do things like that anymore, so it's fine. Maybe as like an extra credit, I might do something like that, but because, you know, we can be meaner on extra credits, but as far as the regular exam is concerned, yeah, don't worry about that. Everyone's okay? Good. So let's talk about the exam. So as I had promised, first things first is Kirschkorn's loop rules here will definitely be a long problem. So this is definitely a long problem with, of course, the sign conventions here. So particularly for the Kirschkorn's loop rule one, it's these two sign rules. We'll leave out the capacitor for something else. So all of this is part of that same long problem. So we'll call that long problem one. Long problem one. So here, basically, the way it's going to work is I'm just going to give you a diagram, just like I did in those group assignments, as well as the practice ones that we did. Just give you a diagram. I'm not going to tell you anything about the direction of the currents. I'm going to tell you, of course, what the voltages are and the resistors are. So you'll have to choose your own directions of the currents. So on there, basically on the diagram, either draw your own new diagram or use the diagram that I give you and make sure you label the currents. You tell me which loops, which directions you're going around, because the first part of the problem will be basically, you know, write down Kirschkorn's loop rules for the equations that you're going to solve. And you're going to get basically most of the points for writing those things down. And then the next part will be, well, now solve for the currents. So, you know, you'll get points for now solving those guys, but most of the points are coming down from applying these guys. So now, of course, there's so many different combinations. Without telling me what directions your currents and things are going through, it'll be a lot harder for me to figure out if what you wrote down was correct or not. So just make sure in the diagram that I give you, you label all your currents, label which loops, label the directions, not only for me, but for you as well. Just make sure that you have all the right directions at which you're going. Good, so that's one long problem. Another long problem will basically involve a lot of this stuff here. So basically a lot of Ohm's law and a lot of drift velocity and all this kind of good stuff. So basically a lot of the stuff here will be long problem 2. My son is coming back. Yes. I'll put all this stuff together here. So long problem 2. Hi.
Daddy, when are we gonna go?
What, to lunch? It's not even 10 o'clock yet.
10 o'clock.
Well, yeah. We'll go closer to 11, so we'll more like in an hour. Go downstairs. I'm almost done. Go. Okay. What was I talking about? Oh yeah. So basically, all this kind of stuff together will then be long problem 2. So it's going to involve a lot of current density, Ohm's law, all that kind of good stuff. And then the last long problem, I'm going to go all the way back here, will basically involve capacitors, but it's going to involve some of this stuff here too. So what color haven't I used yet? We'll use blue this time. Good.
You didn't use blue?
I'm talking in there, not you. Good. So that's going to involve these things here, since this wasn't part of the last exam. This stuff you don't have to worry about, but it's also going to involve stuff with capacitors, specifically these things, also parallel and series. So basically, kind of tell you the way it's going to set up. So long problem 3, long problem 3. So basically, where this one's going to work is part A, you're going to have to do an integral of some sort to then determine the capacitance. And then once you know the capacitance, then you'll have to combine capacitors in series and parallel and then find other stuff about it. But if you don't do the integral well, I'm also going to tell you what the capacitance should be. So that way, in case in part A, you don't actually get what the integral, or at least the value of the integral, I'm going to give you what the capacitances are. So at least you can do the rest of the problem from there. So. Thank you. So these are the 3 then long problems. What about the short problem? So one short problem is going to involve this stuff. So dielectrics mixed with some capacitor stuff like energy storage and things like this. So this is going to be one of the short answers. So short answer 1. Another short answer will then involve these guys, resistors in parallel and series. So this is another short answer. Call that short answer 2. I think the other one is RC circuits. Let me quickly look here because I don't remember. Let's go back. Man. I'm almost done. So let's take a look. Oh, no RC circuits, just general things about like Ohm's law and power and stuff like that. So, good. So the last one is going to involve things like, I went back too far. Good. So part of this will be part of a short answer as well. So short answer 3, things with power, short answer 3, things like this. So basically just general knowledge of Ohm's law and your understanding of power radiated and how all these things work. Which means that the short answer, or not the short answer, but the extra credit will be this stuff. So RC circuits will be extra credits. So any questions on anything? Everybody's doing okay? So as I said, typically this is either the second easiest or the easiest exam for the semester. So this is usually a good place to kind of make up points if you're kind of missing some points here. Typically the easiest exam is the 5th exam, but this one's usually pretty easy too. So it should be a nice place to pick up extra points for anybody who needs points at this stage. So like I said, any questions on anything that I talked about or didn't talk about, or anything I forgot? No, everybody's okay? Alrighty then. So the last thing is 2 things. Number 1, I posted the conceptual questions for today, so they're already posted. You have till 5 o'clock tomorrow to get those done. So those are all dealing with chapter 28 stuff, so circuit stuff. And then tomorrow we are face-to-face again. So tomorrow we will have class. It's cool again. My son just fell out of the chair. That was kind of funny. And then the last thing is, so tomorrow again, we're going to start new stuff. So we're going to start talking about, well, that time was planned. You don't get funny for that one. So we'll start talking about magnetic fields and all that good stuff. So we'll mostly just kind of compare and contrast them to electric fields, and then start talking about forces on wires and all that kind of good stuff. So So no questions? Everybody's doing okay? Yeah, I see a lot of you are in UC at the moment, so okay, everything. Good. Nice. Okay. Everybody's doing good? All right. So I will see everybody tomorrow. See all of your faces again.
Can we please draw?
When I am done, boy. I'm done. Okay. So I'll see everybody tomorrow then. That's my son's driving me nuts. All right.
Draw.
Hey, stop. I'm trying to do stuff here.